probability distributions. Discrete and continuous. First, we'll focus on discrete random variables, which when you boil it down, we can make it pretty simple. Okay. Continuous. We've kind of dealt with continuous random variables. We'll deal with them mostly in the context of a normal distribution. But that's a little bit ahead. I don't think we'll get there today. Today, we are probably going to get to, we'll definitely do this. We'll definitely do that. We'll do that. And then I don't believe we're going to get any further than that. No, I don't anticipate. So that's where we're going to be. All right, so we got some definitions. All right, a random variable. It represents some numerical value associated with each outcome of a probability distribution. So, like if we were going to count sheep, right? The number of sheep counted, the number of sheep that we observed would be, we could make that the random variable x, right? And here's another example that don't involve livestock. Yeah. So a discrete random variable has a finite or countable number of possible outcomes that can be listed, right? For instance, the number of sales calls a person can make in one day. So this is how I would differentiate between the two, discrete and continuous, right? Is it possible for the sales guy to make 4.1 phone calls in a day? No, that's ridiculous. It's weird. How do you make 0.1 of a phone call? Either you made a phone call or you did not make a phone call, right? So that's how we'll be able to tell, right? If you could count it as, hey, it either happened or it didn't, and you can count the number of times that whatever thing happened, right? Then you would call that discrete. It's countable. So a continuous random variable has an uncountable number of possible incomes, okay? Represented by an interval on the number line, that's what it looks like that. So hours spent on sales calls in a day, right? So, for instance, right, if it was hours spent on sales calls in a day, right? There's an infinite number of possibilities for hours spent on sales calls in a day, right? I could spend 1 hour, I could spend 3 hours, I could spend 3.4 hours, I could spend 3.49 hours, I could spend 3.69482 hours, I could spend 5.821692 hours. I could do that all day. I could never stop, right? Talking about or listing different combinations of how many hours I spent on a phone call a day. You know what I'm saying? All right, so let's decide whether this random variable is discrete or continuous. The number of Fortune 500 companies that lost money in the previous year. And really, honestly, for me, the best way to decide this is to say, hey, is it possible for 5.6 companies to lose money? It's impossible. You either lost money or you didn't. You didn't kind of lose money. If you kind of lost money, then you lost money, right? So that's how you'll tell the difference, right? So indeed, this must be discrete. Hey, decide whether the random variable is discrete or continuous. X equals the volume of gasoline in a 21 gallon tank. Is it possible for there to be 6.2 gallons? Yes? It's pretty easy. I mean, For me, that's the easiest way to decide whether it's discrete or continuous, right? So it must be continuous, right? If it's possible that I could have fractions in there, that means that I could have infinite numbers of fractions, right? Since there are, indeed, between 1 and 2, there are infinite decimals. Between 1 and 2. There are crazy. Okay, which one's discrete or continuous? Okay, the speed of a space shuttle. Can the speed of a space shuttle be some sort of decimal? Absolutely. So then it's continuous. How about the number of calves born on a farm in 1 year? Can you have half a calf get born? You just can't, right? If there's either one calf or no calves. So that means that this must be. Alright, so we're going to look at a probability distribution, okay? We're going to list each possible value of a random variable. And then we're going to have a probability of that random variable. And in order for it to be a probability distribution, two things must be true. Each probability has to be between 0 and 1. If it's not an actual probability, right? And you got to be able to add them all up and get 1. This is going to be super clear when we look at a couple examples. Alright, so this is how we're going to make a discrete probability distribution. We're going to have some outcome. Right, so we're going to have outcome like 1, 2, 3, 4, and then we're going to have a probability of each one of those outcomes occurring, right? We're going to look at the sum of these frequencies, and then we're going to actually create a probability. I really feel like actually doing this is going to make a heck of a lot more sense than this explanation. So I want to get to that as quick as possible. So here is an example. We've got a personality inventory test for passive aggressive traits of 150 employees. They're given a score from 1 to 5, where 1 was extremely passive and 5 was extremely aggressive. A score of 3 indicated that they were neither passive nor aggressive. So we're going to we're going to construct a probability distribution for this random variable x, and then we're going to graph this thing. Okay. So here we go. So we look at this. So I'm going to tell you where each of these things come from. If we look at this, we're going to get our total here. Our total is 150. It says it. I don't know why I was looking for the equation. Right? So this adds to 150, right? So then this, the probability of getting a 1, a score of a 1 is going to be 24 out of 150. And then this one is 33 out of 150. This one 42 out of 150. 30 out of 150. 121 out of 150. We'll calculate all of those and get some decimals. I'll just go ahead and do that right now. I'm going to extend this thing. Go ahead and make these calculations. So, 0.16. Probability of getting a 1. 0.22 is probability of getting 2. 0.28 probability of getting a 3. 0.2 probability of getting a 4. And then our super aggressive people, there are 0.14. 14% of them are highly aggressive. These are our road ragers, I think there. Alright. So, we'll write that out in a different way. So we're going to flip that thing, right? So that's the score of a 1, that's the score of a 2, that's the score of a 3, score of a 4, score of a 5, right? And then each of the probabilities associated with them. So when you see a discrete probability distribution, it's always going to look like this, with your x and your probability of x. And it looks like, for all of you algebra people, you might want to say p of x, but that's actually the probability of x. Probability of a 1 occurring. Alright, we've got to check to see if this is actually a legitimate probability distribution. Number 1, is each probability less than 1, or between 0 and 1? Yes. Right, so each probability is between 0 and 1. Sure. 2. Do they all add up to 1? So is 0.16 plus 0.22 plus 0.28 plus 0.20 plus 0.14 equal to 1? Well, let's see, 0.16 plus 0.22 plus 0.28 plus 0.2 plus 0.14. Bam, it is. Check. This is a probability distribution. You are definitely going to be asked to check if a probability distribution is a legitimate probability distribution. Probably many, many times. It's a very common statistics question. And what are you going to do? You're going to check these two things. And I guess I'll be on the function. If we were to graph it, this is what it would look like. We'll actually do one on our calculator. I hope we're out of time. The next thing we're going to do is we're going to create this graph. And here we go. So, we're talking about number of sales, new employees, number of sales of new employees, maybe, during a 100-day probationary period. The results for one employee are shown. Let's look at the probability distribution. Okay. So first of all, I really want to put this into context. Okay, 100-day period. going to interpret this then as 0 sales, right? So X is our number of sales, right? So this X, I should say right there is better, right, is number of sales. Sorry, days was in my head just now. Number of sales. And this then is going to be the number of days. Yes. This is the number of days for which this person had that many sales, right? So 100 total days. So how would we read this particular row? We would say that this particular salesperson made 7 sales for 2 of those 100 days, right?